Hey physics, this is Mr. Hausman. I'm trying to do a little pen cast to help those of you who might be catching up on the vector lab or getting it started from the first time. If you hear some clicking in the background, if my microphone's picking that up, that's because my dog Riley is chewing on her favorite antler and she's having a good chew, so please ignore. So first thing first, you've been asked to do this lab to demonstrate your proficiency with vector addition, both graphically, it's got a pen color that we can actually see, graphically and algebraically. We're going to be adding vectors to find the resultant. A resultant vector is a sum of vectors. And you're thinking to yourself, perhaps, that vectors must be able to be added just like any other numbers. And that's not quite true, because as you know, vectors have magnitudes and they have directions. So let's take a look. So say you've drawn a few cards, maybe vector A and B, or maybe you're also have been asked to do a third card. And maybe you drew at random, but perhaps what you did is you drew a 7 centimeter vector at a 45-degree angle. And that's obviously not drawn to scale. You would try to do it with a protractor. And then maybe a 9 centimeter vector, but this is at a negative 40-degree angle, or 40 degrees below the horizon. And just for, to make it pretty challenging, let's make a third vector be directly on the y-axis. It has no x component at all. And let's make that a 4 centimeter magnitude. Now, its angle is actually 90 degrees relative to the positive x-axis, right? 90 degrees rotated. And those may or may not be real cards in the actual bucket of cards, but we're going to still practice with these. So you first have to measure them and put them on your data sheet here. Please don't draw on the cards themselves, even though they're laminated. We find that they hold the ink or the pencil marks. So what you're doing is going back to your original vectors: 7 at a 45-degree angle, 9 at a negative 40-degree angle, and 4 centimeters straight north at 90 degrees. And that's right, 45 degrees. Go back. Oh, it was 4 north. Let's move on. So there is a little bit of flipping and flopping back and forth. But your first task, if you are going to do algebraic addition, is you realize that there is no way to add a vector that's north and east and south and east and then another one north all at the same time. So step one is to take your vector, your first vector, I believe it was 7 centimeters at a 45-degree angle, and to break it into its x and y components, x and y. And you don't do your work here in these boxes, but rather what you do is you maybe split this box in half and do your calculations for your x component. That would be cosine of your angle theta times the hypotenuse. And for the y side, this y component, or the opposite side of this vector triangle, that would of course be sine of theta, because it's opposite the 45 times the hypotenuse. If that's too quick or that's not clear where those come from, please let me know or follow up with me. So we've got first vector done. Now you have to do the same with the vector letter B. So its x component and its y component. You'd use the exact same formula, just changing theta and the hypotenuse. And if you have a third one, you also have to do an x and a y component. And all of your data goes here for the x's and y here. And why are we putting them in columns? Well, the very next step is going to find the sum. And another way to write that is a sigma. Sigma is the Greek letter. We've used delta numerous times before, but you need to add up all the x components and all the y components. That third vector, I believe, has no x component at all and only had a positive y. So sometimes your x component can be 0 centimeters too. So you've got your sigma x and y. And you could actually say that that is your resultant. But that would be called rectangular notation. That is your resultant. But in reality, when someone says find the resultant, what they really mean is to probably turn it into polar notation, where you give a final magnitude and an angle. So when they add up to one number in the x and one number in the y, people are going to say, yeah, that's okay that you tell me it's x and y, but I just want to know really what is the total vector. So say you have, and I apologize, I'm not going to do this with real numbers, you have a positive x of 3, and you have a positive y of 4. Well, we are still adding them, but what you notice is that the sum, and notice I connected them head to tail, and I did that just so you could see, here is the resultant. These, of course, should all be done with rulers. And when you calculate the length of this side, you are now calculating its magnitude. How big is that vector? The last step is to find the angle that's in your final resultant to figure out how many degrees above or below the horizon. So I'm going to say it anyway. The R is, of course, a hypotenuse of a right triangle. So you're going to get your sum of your components, x and y, turn them into the A and B sides of this triangle, and of course take the square root. And to get theta, you're going to be using probably inverse tangent of the opposite over the adjacent side. We have an opposite and an adjacent right there. So when you're done, you're going to have a final magnitude and a final angle. And how you usually write that is not with these square or angular signs, but rather simply with parentheses. You always do magnitude first, MAG, comma, the angle. Now, you don't want to just do that in the box. You want to do the actual work in that box, do the Pythagorean theorem, do the inverse tangent of the opposite side over the adjacent side. But somewhere at the bottom, make sure you have provided the polar coordinates. Adding the components, like the sigma x and the sigma y, no. Let's go over here. We'll check this 7. Lastly, and this is where maybe some people are a little uncertain of what they're adding here. This is not a graph, but it's called graphical addition. Really, it is a scale drawing. It has to be done precisely with a ruler and a protractor. But the question is, should I? And all you have to do is connect your 3 vectors head to tail. You can do it in any order. So let's say the first one is a 40-degree angle of 7. And we know that 45 degrees kind of goes through the diagonal of these boxes. So with a ruler, make it nice and straight and make it 7 centimeters. I can do that better. Let's make it 7. Whoops. Let's undo that. Let's make it 7 centimeters. I would make it about that long. Then the next one was 40 degrees below the horizon, but we have to connect it head to tail. And that's going to be a little tricky. So what you do is you create an artificial Cartesian coordinate plane, x and y axis, flip your protractor over now, and now you're going to be representing the 9-unit vector that's at a 40 degrees below the horizon. And I'm currently guessing, and that's not acceptable. You don't really guess, okay, with a ruler. And to go 9 might go right off the page. So let's label this 7 centimeters at a 45 degrees, 9 centimeters at a negative 40-degree angle or 40 degrees below the horizon. And then the last one, I think I want to try to stick with it, see if I can. Okay, so 4 centimeters straight north. Let's change to black just to add another color. So 4 centimeters straight north. That's a little, maybe longer than 4 centimeters. And that would be all 3 vectors connected head to tail. Yours should be ruler precise. Now to finish, what is the actual sum? Well, these 3 vectors are describing where you went at different angles and different magnitudes, and you finished right here. So your total resultant would be a straight line path from the tail of your first vector, tail of first, to the head or the arrowhead of the last one. And now your resultant vector is itself a vector, so make sure it has an arrowhead as well. And you would have to measure the length of that line, so actually measure the magnitude and measure the theta. What is the angle that's created to your resultant? Now, what's this box for over here? Well, this is your answer to the final box before. What is the magnitude and what is the angle? But on this side, you did it all by mathematics. Now, if you do it really well and you do your scale diagram to like really high quality, then these 2 methods should come up with very similar answers. And we found students that had them within like a millimeter of each other, and the angle was within a single degree off. But fundamentally, these are just 2 different ways of adding vectors. Most people like the algebraic method, but in this case, the graphical method could have probably gotten you there a little bit quicker. So thanks for watching. Hope that helps you get started or continue your work.